Okay, so any questions?
Hocam bu area dediğimiz şey bu yerin iz düşümü değil mi yani? Normalde
No, any area. Now, you have to also distinguish between the area and the area vector. The area vector is a vector perpendicular to the point, perpendicular to the surface at the point that it is evaluated. So, if we take this, in the case of this example, you can talk about the area vector over here, this dA. It is in this direction. The area vector over here is in this direction. Its direction always changes. At every point, you have a different vector dA. If the area is bending, dA will be different.
Hocam o zaman burada bu amper yasasını nasıl uygulayacağız? Simetri yok.
You see, the two things that you have to distinguish is whether it is correct or not. The Ampere law is correct, whatever the surface is. The other thing is whether it is useful. If it's not symmetry, this form of the Ampere's law, this form of the Ampere's law is, as you said, not much useful. It is still true. Whatever the surface is, whatever the closed loop you consider, it is always true, but not always useful.
Gösterdiğiniz alttaki şey var ki, burada hocam kapalı yüzey olması mı yani?
No, the surface is not necessarily closed. This is not a closed surface. This is an open surface. And this open surface has a boundary. In fact, this says that if you have a closed surface, I mean, this law, this relation you can also apply in a closed surface, but the closed surface doesn't have a boundary. So if you take the curl of any vector field, integrate it over a closed surface, that will always be zero.
Can we find any relation between Ampere's law and Ohm's law? I mean, can we derive one from each other?
No. Now, we didn't discuss the currents in detail, but Ohm's law in terms of the currents is this one. If you have a conductor, if you create an electric field inside your conductor, and hence creating this current, the current density at a given point will be proportional to the electric field at that point, and the proportionality constant is what we call the conductivity of the material. We will come back, we will come back to this point later. Probably not this semester, but next semester, probably. So now we know the curl of B. So how many of you remember the Helmholtz theorem? In electrostatics. So we were looking at the curl of the electric field and also what else were we studying? Divergence of B. Now, the Helmholtz theorem basically states that if you know the curl of a vector field, the divergence of a vector field, and if you know the boundary conditions, then you can uniquely determine the vector field. So that is what will be our purpose, determining this B field. So we already know the curl. Now we need to evaluate the divergence of B to be able to determine the B uniquely. Again, we just go back to our expression for the B field. This was mu 0 over 4 pi integral of j of r prime cross r minus r prime over r minus r prime cube overall volume Let's take its divergence. Well, this is equal to mu0 over 4 pi divergence of j prime cross r minus r prime over r minus r prime cube. Again, I repeat, this is the divergence with respect to the coordinates of r, not r prime. And j prime only depends on r prime. Now we will basically use similar tricks. The strategy will be somehow move this divergence to here, take the derivatives, consider the derivatives of this one. But the derivatives of this one, instead of taking the derivative with respect to the coordinates r, we can replace it with derivatives with respect to the coordinate r prime. And once we change these derivatives with respect to derivatives with respect to r prime, we can use integration by parts. And to simplify it such that the surface terms will just give us 0, and we will see what remains. That will be our strategy. Now, first, let's try to move this derivative to here. Now, the divergence of j prime cross r minus r prime divided by r minus r prime cube will be just derivative with respect to xi of j prime cross r minus r prime over r minus r prime cube. But the I component of that, which will be derivative with respect to xi of epsilon I jk, j prime j, xk minus xk prime over r minus r prime cube, which will be epsilon I jk, jj prime, derivative with respect to xi of xk minus xk prime over r minus r prime cube. Now I'm taking the derivative of the difference of r and r prime. But this, I know that I can just change the derivative with respect to xi prime to derivatives with respect to x. I'm taking the derivative with respect to xi. I can change it to derivative with respect to xi prime with a minus sign. Minus epsilon I jk, jj prime, del over del xi prime, xk minus xk prime divided by r minus r prime cube. Now, I will be, as I said, I will be doing basically integration by parts. Here. You see, here I'm taking derivative with respect to xi. Here I'm taking derivative with respect to xi prime. Let's say this will be equal to minus epsilon I jk, derivative with respect to xi prime, jj prime, xk minus xk prime over r minus r prime cube, plus or minus derivative of jj prime with respect to xi prime of xk minus xk prime over r minus r prime cube. Well, it will be long in this way, so I will change my method. Okay, we didn't do anything wrong, but proceeding in this way will take us a long time, so let's do it in a different way. So let's go back to our B. Mu 0 over 4 pi j of r prime r minus r prime over r minus r prime cube dv prime. Well, you see, this is nothing but the gradient of 1 over r minus r prime with a minus sign. Gradient with respect to the coordinates of r. I mean, you can just think of this as the electric field of a point charge. The electric field of a point charge is nothing but minus the gradient of the potential of that point charge. So this is something you should remember from electrostatics. Now I can take this is derivative with respect to the coordinates of r. I can take this out of that integral, out of the v prime integral. So if I take it out, it just becomes mu 0 over 4 pi times the curl of j of r prime over r minus r prime. Well, you see, I have a minus sign over here. I don't have a minus sign over here. That's mainly because essentially I'm changing the order of this del operator with the j vector in their cross product. So that brings an additional minus sign, so that this minus sign over here just disappears.
Hocam şurada kare olması gerekmiyor mu?
Here? No. The potential is just 1 over r. That is the electric field, which is 1 over r squared. Well, I'm done. The B field is the curl of some other vector field. If you take the divergence of a curl, let's say the curl of, let's call that A, this is always equal to 0 for all vector fields A. So since B, I can write it as the curl of this thing, del dot B is equal to 0. Always. So now this is our second equation. We already had calculated the curl of B, which was equal to mu 0 j. Now we know the divergence of B, which is 0. So based on Helmholtz theorem, this states that we can determine B given some boundary conditions. Now you see this B is equal to curl of A, where A is equal to mu 0 over 4 pi j of r prime divided by r minus r prime times dv prime. Well, essentially it's like a potential. You see, if you remember electrostatic potential, the way we defined the electrostatic potential was we had this charge density evaluated at the point r prime, divided by the distance of my point r to that point r prime, summed over all r prime. It just looks like the electrostatic potential, with the only difference that the charge density is replaced by the current density. Since this is a vector, the potential also becomes a vector. This is called the vector potential. It doesn't have an interpretation like the energy as in electrostatic potential. It is just something we can express B in terms of.
Hocam şimdi Hani burada dedik ya bundan yardımıyla işte manyetik alanı belirleyebiliriz. Peki şurada bulduğumuz manyetik alan mı?
Well, you see, in this problem, for example, this is what you are talking about, right? So we could determine this one without really worrying about the divergence of B. But the symmetry of the problem, and I mean, you see, we said one thing. We use the symmetry of the problem. How did we use it? We first said that, okay, B cannot depend on phi, B cannot depend on Z, the magnitude. So the magnitude can only depend on the distance. Then we had to determine the direction. We said that, okay, it cannot start from the wire and go radially out. Why not? Because the divergence of B is 0. It cannot start at a point. So when we said that B has to form circles around the wire, we already used it. We used the fact that the divergence of B is 0.
C'nin diverjansı niye sıfır? C'nin diverjansı.
Because we are looking in magnetostatics and electric charge is conserved. You see, this is true as long as the charge is conserved. So since we are in statics, this derivative is 0. So the divergence of J has to be 0. You see, if divergence of J is non-zero, you can think of it as J starts from point and it's going out from that point. But if all the currents are going out of a point, that means the charge at that point is getting less. No charge is entering that point. All the charge is going out of that point. So the charge density at that point is changing. But that means it's not a static problem. So in electrodynamics, divergence of J will not be 0. But since for the time being, for this semester, we are restricting ourselves to static problems, divergence of J is 0. Otherwise, it would mean that there is accumulation of charge in a region, or the charge will be moving out of a given region. So the total charge in that region would be changing if the divergence of J is non-zero at a region.
Hocam bu fiziksel olarak var olabilen bir sistem değil mi? Yoksa ideal olarak mı düşünüyorsunuz?
Well, of course, this is some kind of an idealization. If you consider the real charges, I mean, the charges are inside atoms. In the atoms, the electrons, semi-classically, they are always moving around. They are never at rest. But the problem is, statics is never a reality. It's an approximation. And as every approximation, there are corrections to this approximation. Now, the corrections will be proportional to the speed of the charges. But of course, then the problem is you have to compare the speed of charges with some other speed. You cannot just say that speed is large or small, unless you compare it with something else. So then the question is, what should we compare it with? If you consider all the laws we have the electric field, let's say, of a point charge, 1 over 4 pi epsilon 0, q r minus r prime over r minus r0 over r minus r0 cube. The magnetic field, let's say, of an infinite wire, this is equal to mu0 over 2 pi d I in some direction around the wire. So these are the, let's say, in a sense, fundamental relations related with electric fields and magnetic fields. So, and we want to find a speed to compare the speed of our particles with. So what should we compare it with? Now, what is the unit of epsilon 0? Well, look at that equation. If you multiply E by Q, the force should be Q squared R minus R prime over R minus R prime cube divided by 4 pi epsilon 0. Well, unit-wise. Well, if this is so, then the unit of epsilon 0 should be Coulomb squared divided by meter squared times Newton. This is our unit of epsilon 0. Now, what is the unit of mu 0 in terms of Coulomb, newtons, meters, etc.? Well, let's start with the unit of the force is the same thing as the unit of Q V cross P. Well, in fact, let's do one thing else. These are true. Let's look at this one. Force is Q times E plus V cross P. This is the Lorentz force. Well, this basically tells me that unit of the electric field is equal to unit of the velocity times unit of B. So if we want to find something that has the unit of a velocity, it is the unit of electric field divided by unit of B. Well, the unit of electric field is the same thing as the Coulomb squared divided by meter squared times the unit of epsilon 0. Because electric field is 1 over 4 pi epsilon 0, Q squared divided by meter squared. Divided by, well, the unit of magnetic field is unit of mu 0 times the current is Coulombs I over 2 pi d. It is the Coulomb divided by meter. Seconds. So this is equal to 1 over the unit of epsilon 0 mu 0. Well, if I didn't do any other mistake somewhere, this is seconds coulombs per meter. Well, let's see, where did I do the mistake? The electric field is not Coulomb squared over meter squared, it's Coulomb over meter squared. So the unit of velocity is equal to 1 over the unit of epsilon 0 mu 0 times 1 over the unit of velocity, or the unit of velocity is equal to 1 over square root of epsilon 0 mu 0, the unit of that one. So, okay, these epsilon 0 and mu 0 constants, we just define them with some strange numerical values, but with some units. But it just turns out that those things, if you multiply them, take their square root, take 1 over them, you get some quantity that is related, that has the same unit of speed. Well, this is a characteristic speed of electromagnetic processes. It's a property of electromagnetic processes, this speed. And 1 over epsilon 0 mu 0, if you just put in the numbers, it just turns out to be 3 times 10 to the power 8 meters per second, approximately. So do you know this number? Speed of light. So what is static? As long as your charges are moving at speeds much slower than the speed of light, you can treat your system as a static system. treating it as a static system is a good approximation because corrections will be proportional to the speed of your charges divided by the speed of light. So yes, exactly static systems is an idealization, but it's a very good idealization for most practical purposes. We can even treat time-dependent circuits using our result in electrostatics. So even for this electricity, which changes 60 times a second at 60 hertz, static approximation is a good enough approximation. Because the charges are moving much slower than the speed of light. Then there is the question, okay, this 1 over square root of epsilon 0 mu 0 is a speed. Now just think about the time of Maxwell or Ampere or Faraday. So there is this speed, but you have Galilean relativity, you know Newton's laws, you are aware of reference frames, and you know that speed is a frame-dependent quantity. The speed of an object will be measured by some value in one reference frame. It will be a different value in a different reference frame. But this speed of light is with respect to which reference frame then? Okay, there is this speed. Okay, fine, but with respect to which reference frame?
With respect to F, and with respect to someone who has zero velocity.
You see, zero velocity with respect to what?
With respect to us.
To us. Why are you so special? I mean,
Us, whatever.
You see, there might be aliens in Andromeda galaxy. Should they worry about your speed? Okay, so what should be their law? There are infinitely many inertial reference frames. If you have one inertial reference frame, any reference frame moving at constant velocity relative to that inertial reference frame is an inertial reference frame. And all of them will measure the speed differently according to Galilean relativity. So how is it possible? Again, we are thinking at the time of Maxwell. There's no special relativity yet.
Reference frame is not important here. The speed of light is...
Is it not? Or are we assuming a reference frame implicitly without being aware of? That was the first approach of people. They thought that, okay, in driving these Maxwell's equations, we didn't pick up on purpose a reference frame, but implicitly, unaware of it, we were talking about a particular reference frame. And they said that let's call that reference frame the reference frame in which the ether is at rest. So that was the first idea of ether. Another problem was, next semester we will be studying electromagnetic waves. Now wave phenomena, until that point, wave is always travels in a medium. Something is oscillating. So you just take, a cable, oscillate it, and you have the waves propagating along this cable. So in electromagnetic waves, what is oscillating? The answer was again ether. So it was a great idea. It resolved all the problems. It answered our question, what is this speed relative to? Well, the reference frame of the ether. Plus, what is oscillating in electromagnetic waves? Ether is oscillating. But then we should be able to measure the changes in the speed of light. As the Earth is moving in ether, its speed is different. Its speed in different directions will be different. So light propagating in one direction should have a different speed than light propagating in some other direction. And then we have this Michelson-Morley experiment, which measured no such difference. And then Okay, the rest is kind of history. You have this special theory of relativity, general theory of relativity, etc. But it all starts from some basic observations. Here we have a speed. So with respect to what? Okay, let's continue. Let's do some other applications, some other examples. Now, we will deal with this vector potential in more detail next week. So that's why I'm kind of skipping it over. There is this quantity called the vector potential. Just like the electric field, we can write it in terms of the derivatives of a scalar function, the electrostatic potential. We can write the magnetic field as the derivatives of some other, this time, vector function, which we call the vector potential. Just keep that in mind for the time being. Their expression in terms of the vector current is also quite similar to the expression of the electrostatic potential in terms of the charge density. You have this overall coefficient. Take the vector current divided by the distance, integrate over all your sources. Now, let's do some simple examples on Ampere's law. B dot dl will be equal to mu0 times I enclosed around any closed loop. Now let's take this example of an infinite planar sheet that has a uniform surface charge density. It is infinite in every direction. And it has a surface charge density sigma. Let's say it is in the xy plane. X, Y, and Z. And let's just assume that it is moving with a velocity v in the y direction. Now, first question, is this a magnetostatic problem? V is constant.
If V is much smaller than the speed of light,
If it is much larger, it's comparable to the speed of light.
Eğer yük değişmiyorsa
The sigma is constant. You see, if you wait, this is your infinite plane. If you wait some time, it will be just displaced by some distance. This is your infinite. Nothing changes. So whatever the speed v is, nothing changes in time. There is a current. Okay, it's not, the system is, okay, there is this word wrong usage of terminology. The system is not static. It is more precisely described as steady. Nothing changes in time. Static means no motion, basically. There is motion here. The plane is moving. But nothing changes in time, so it's steady. Okay, first of all, if we want to use the Ampere's law, we have to identify some properties of the magnetic field. In general, it will depend on the x, y, and the z axis everywhere. Let's look at the magnitude of B. So if I translate my system along the x, does my system change? Or let's say, rather than putting my origin over here, let's say at this point, I just displaced it by some distance along the x-axis. So all the points will have a different x-coordinate now. Nothing will change, so the magnetic field of that point shouldn't change if I change the x-coordinate. So it cannot depend on x. B? Well, similarly, it cannot depend on Y. So B, the magnitude of B can at most depend on Z. We don't know whether it depends on Z or not, but just from the symmetry, we cannot eliminate the possibility that the magnetic induction can depend on Z. So now let's look at the direction. What should be the direction of B?
Yukarı ve aşağıya.
Well, let's see. Your friend is claiming that it should go this way. But that means the magnetic field line should start at the plane, right? But divergence of B is equal to 0. So it cannot start at that on our plane. It cannot start at any point. The magnetic field lines should either form closed loops or they should extend to plus and minus infinity. They cannot start on the plane. They will be parallel in the x or the y direction or in some other direction. Minus x, well, your friend is claiming that it's in the x direction, whether in the minus or plus x direction. But you see, let's look at the expression of B. We will not be evaluating it explicitly, but it's mu 0 over 4 pi j at the point r prime cross r minus r prime over r minus r prime cube. What is the direction of j? J is in the y direction. If j is in the y direction, you take a vector that is in the y direction, take its cross product with some other vector, the cross product will always be perpendicular to the y direction. Of course, it can be in the x direction or z direction or any superposition, but it cannot have a component in the z direction because that would mean it starts from the plane. At least one component of it starts from the plane and goes to infinity. But it cannot never start from the plane. It should extend until infinity. So it cannot have a z component also. It should be along the x direction. Now let me plot it like this. This is my x-axis, this is my z-axis, and the y-axis is pointing towards us. So the surface current density is towards us. Well, another thing you can think of is we have already the case of infinite wires. If we have an infinite wire, infinitely thin infinite wire, well, this plane, you can just think of it as just a collection of infinitely thin infinite wires. Now, if you consider this segment as a very thin wire, it will create a magnetic field at this point, magnetic induction field at that point, and the direction of that magnetic induction field will be. You see, I have this plane, I'm dividing it into very thin wires, and I pick one of them, and then I choose this one, the contribution to the magnetic induction at that point from this very thin wire, what will be its direction? I is out of the screen. You see, this plane is moving towards you. So just your thumb in the direction of the current. Wrap your fingers around this wire. So this is the direction of the magnetic induction due to this current running through this very narrow strip. But I have another segment over here, right over here, symmetrically positioned. And the contribution to the total magnetic induction at this point of this very narrow segment will be In which direction? This one. You see, this vector over here is perpendicular, so if you consider this line, its contribution will be in this direction. You see, both of these wires, since their lengths are equal, their distances from this point are equal. They contribute with their contribution have the same magnitude. It's just this, they make a different angle, but they both make the same angle with the horizontal. So when I sum the contributions of these two, they will add up to be a horizontal vector. So for any such very narrow segment, narrow strip, you can imagine a symmetrically positioned strip, so that when you sum the contributions of the two, you will end up having a contribution horizontal to my plane.
Hocam bu küçük parçanın yönünün hangi taraf, yani diğer hangi yön?
You see, the current is running in this direction. So this strip is also, and you see, just think of it. I have this plane. It has some uniform charge. It is moving in this direction. And I'm taking a very narrow strip over here, infinitely long. So it is moving in this direction.
O zaman bu diğer K'ye de paralel olmuyor mu?
No, it is, well, you see, the wire is parallel to K. You see, the current in this wire shouldn't leave my wire. So this wire is always parallel to my K. This very narrow strip will always be parallel to K. B field will be perpendicular to K. K is the surface charge density.
Ya benim kafam şeye takıldı hocam, şimdi bu K dediğimiz şey diğerde dik olması gerekiyor ya. Ama burada diğer paralel.
You see, here, this is my DL. Or let us look at it from the top. This is the top view. Okay, so in this view, this is moving in this direction, let's say. Y is in that direction. This is my x vector. Z is pointing up. Okay? So my strips are these ones. This is my K. I am taking this length as my L, which is perpendicular to K. I'm not considering a segment of the wire. I'm taking the cross section of that wire. Since this is just a plane, the cross section of this very narrow strip is a line segment of length L. Any other questions? So now, are you convinced that the magnetic field above this plane is horizontal and in this direction? Well, I can repeat the same argument for this other point over here. This segment will create a magnetic induction at this point in that direction. And this segment will create a magnetic induction at this point in this direction. The sum will again be horizontal, but in the other direction. Now, furthermore, if you assume that this distance is the same as this distance, then all these distances will be equal to each other. And the magnetic field at this point, its magnitude, will be equal to the magnetic field at this point, the magnitude of the magnetic induction at this point. So now what we know, the magnetic induction, the magnitude, first of all, depends on Z. It can depend on Z. It will be in the, either in the plus X or minus X direction. Well, we already seen that it will be above the plane, it will be in the plus X direction, below the plane, it will be in the minus X direction. And we also know that it doesn't depend really on the value of Z, but on the absolute value of Z, the magnitude. Because the magnitude of magnetic induction will be this, at this point will be the same as the magnetic induction at this point. These 2 points have different Z values, but the absolute value of their Z values are equal. So those are the things that we know before applying the Ampere's law. These things we should know before being able to use the Ampere's law. If we cannot extract this information, Ampere's law is useless. It is correct, but useless. Okay, any questions on these? Well, our time is up, so I will just stop here. And we will pick up from here next week. So if you have any questions up to this point. Okay.
Bu correction'ı uyguladığımız bir sistem var mı? Hani çünkü biz statik kabul ediyoruz buna kıyasladığımızda.
Well, I mean, in particle physics, you have to use those corrections. For example, in accelerators, you have to use those corrections. If you want to study ultra-high energy cosmic rays, you have to use those corrections. If you want to study circuits, forget about them. Okay, so see you next week. Have a nice weekend. And your second midterm date is approaching on the 24th of December. It's something like 2 weeks from now. Not next weekend, but the following weekend.
We are just 15.